Hello students, welcome to my lesson of waves. My name is Wanda Ronald. I'm from a company called Professional Education Consultancy, which has put in place a virtual school in the name of PECO Virtual School PVS. The topic is waves. This topic in physics is taught in senior 3. Sometimes when the teacher has delayed, can bring it in senior 4. But it is basically a senior 3 topic. Waves is something that you have ever seen or you have ever heard, but I'm very sure that you have ever seen a wave. But let us introduce it like this. When a stone is dropped in still water, ripples spread out in form of concentric cycles. These are ripples here, and you can see they are making cycles. They spread out. When a stone is dropped here in water, which was initially still, then there will be ripples in form of concentric cycles around the point where the stone enters the water. And if a floating body is placed in these ripples, it starts to move up and down, trying to tell us that the molecules of water are moving up and down with the energy received from previous molecule, and in so doing, energy is transferred to the next molecule. Also, when you hit something like a desk, anything metallic, like I'm going to hit, sound is produced, but the particles do not move from the desk to our ears. What we only receive is the sound. No particle of what I have hit moves from the medium I have hit to our ears, but sound is heard. Now the sound heard is the wave. The sound heard is the wave. Also, looking back at the example of a stone, when the stone is dropped in water, those ripples, after some time, the water clears and it goes back to normal. It becomes still. So with this, help us to understand our definition of a wave. What is a wave? A wave is a disturbance of a medium which results in the transfer of energy from one point to another, but without permanent displacement of the particles of the medium. I want to emphasize without permanent displacement. The keywords: there is a transfer of energy from one point to another, but without permanent displacement of the particles of the medium. What do we mean by this? When sound is heard, due to the disturbance of the medium, the particles did not move, but they were disturbed. For example, even the water gets disturbed and forms water waves, but after some time the particles settle back. That's why the water becomes back still, or gets back to become still, and in that case there was no permanent displacement, and therefore a water wave was formed. So a wave is a disturbance of a medium which results into transfer of energy from one point to another without permanent displacement of the particles of the medium. What are the types of waves? There are basically two types: mechanical waves and electromagnetic waves. We are going to look at each of these individually. What are mechanical waves? From the word mechanical. Mechanical waves are waves produced by a disturbance of a material medium. When you disturb something material like air, anything that you can touch around where you are seated, and a wave is produced, that wave is called a mechanical wave. Mechanical waves require a material medium for their transmission or to move from one point to another. They cannot move in a vacuum where there is no medium, or they cannot move in free space. This word vacuum is also called free space in physics. So the mechanical waves are produced by disturbing a material medium, and they require therefore the medium for them to move from one point to another. What are these examples? I guess you can already tell the examples of mechanical waves because I've already illustrated some in our introduction. And the examples are the water waves. What was disturbed? Water, by you dropping a stone there. Sound, you hit something, you hit a desk, you hit a metal, you produce sound, and therefore there was a material medium which was disturbed. Seismic waves like the tsunamis, that is still water which is disturbed. Earthquakes, the earthquake, waves in strings, for example like guitars, you hit a string and produce sound, and those are mechanical waves. Let's look at electromagnetic waves. Electromagnetic waves are produced by electric and magnetic vibrations with very high frequency. Now, the electromagnetic waves, from the name electromagnetic, they are actually caused by a disturbance of an electric field combined together with a magnetic field, and disturbing them at very high frequencies. The waves that are produced due to the disturbance of this medium do not need a material medium for their transmission. Do not need a material medium for their transmission. They therefore can freely move through a vacuum. So electromagnetic waves move through a vacuum as opposed to mechanical waves. They are produced by oscillating electric sparks, and very hot bodies. Any particular range of wavelength of electromagnetic waves is called a band. A particular range of this wavelength. We shall understand these terms wavelength with time. But below, let's look at the examples of electromagnetic waves. Now, this one is called an electromagnetic spectrum, which is going to give us the examples of electromagnetic waves. We have gamma rays, X-rays, ultraviolet rays, then we have the visible light. This colored part is giving us the visible light, infrared radiations, microwaves, radio waves, and TV waves. All these waves on this spectrum are electromagnetic waves. We shall look at these electromagnetic waves in detail later on. Now, having looked at mechanical waves, examples, their definitions and explanation, we can now look at the differences between mechanical waves and electromagnetic waves. and I guess you can already isolate out or identify the differences between the two. But here are some. Of course, we said that mechanical waves require a material medium, and here these electromagnetic waves do not require a material medium, hence they travel in a vacuum. Now when you look at the speed of the mechanical waves compared to electromagnetic waves, the mechanical waves travel at a low speed. However, the electromagnetic waves travel at a high speed, and their speed is common to all of them, is the speed of light. All of these examples of electromagnetic waves we named above travel at the speed of light, which is very high, 300 million meters per second. They are produced by disturbing a material medium, as we said before, while these ones are produced by vibrations of electric and magnetic field. Those are the major two types of waves. We now look at the other classifications of waves. The other classifications of waves, we shall have progressive waves, and we shall have stationary waves. From the word progressive, they move, and stationary, they are at rest. So what are progressive waves? These are waves that transfer energy from a point source to a surrounding area. They move energy in the form of vibrating particles or fields. And there are two types of these progressive waves. One, transverse waves. Transverse waves are the waves whose vibration of the particles of the medium is perpendicular to the direction of the wave. We are going to illustrate this. The vibration of the particles of the medium is perpendicular to the direction of the wave. We're going to have an illustration of a transverse wave. A medium like water has particles. Water has particles, and when water is disturbed, its particles vibrate. Now as they vibrate up and down, move up and down, the energy is transferred horizontally, and the direction of the energy is perpendicular to the direction of the vibration. And a transverse wave travels like this. This is how a transverse wave travels. As it moves from the left to the right, the particles of the medium will be moving up and down as represented by these arrows, up and down, hence forming a transverse wave. This is the direction of the wave motion, that is the energy, the direction of the energy, and this is the direction of the energy, and this is the direction of the vibration of the particles, which is up and down, and then that produces a transverse wave. So it is simply a wave in which the vibration of the particles of the medium is perpendicular to the direction of the wave motion. These diagrams illustrate, like for example, a rope. When you keep moving a rope which is fixed at one end and you keep moving it up and down, you produce a transverse wave. They'll be moving up and down here, and the energy will move in this direction of the wave, forming a transverse wave. Now this transverse wave will have points which are called crests, and upper points called crests and lower points called the troughs. This is a trough, this is a trough, this is a crest, and this one is also a crest. We shall look at these terms later, but you know that a transverse wave forms crests and troughs. What are the examples of these transverse waves? We have water waves. Now, all the waves that we mentioned in an electromagnetic spectrum, all those waves, all electromagnetic waves are transverse. But when you are giving an example, you don't say, oh, you just say, list them, list the examples of electromagnetic waves like light, radio waves, microwaves, and etc. Now, hope you've understood transverse waves, which are part of the progressive waves, types of the progressive waves. Now, let's look at the second type of a progressive wave, which is longitudinal wave. Longitudinal waves are waves in which the particles of the medium vibrate parallel to the direction of the wave motion. The particles of the medium vibrate parallel. It is the opposite. The other one, they were vibrating perpendicular, but here the vibration is parallel to the direction of the wave motion. And this forms compression regions and regions of rarefaction. Now, an illustration of a longitudinal wave. A longitudinal wave forms regions which are spread apart and regions which are compressed together. Now, this region here is a compression region, and this region is called the rarefaction. This region where the particles are spaced is called rarefaction. Examples of these include, the major example is the sound waves. The sound waves are longitudinal, but there are also waves in slick springs. Waves in springs produce longitudinal waves. Like I said, a longitudinal wave, the vibration of these particles will move from left to right. The particles will be vibrating from left to right as the wave is moving from left also to right. Now, the particles vibration is to and fro. As they go from left to right, they come back to left, to right, but the energy will be moving. If the wave started from left, then the energy will be moving from left here to right, but at the end it forms regions of rarefaction, which are represented by R, and regions of compression, just like we formed the crests and the troughs in a transverse wave. This is another clear example showing diagram showing a longitudinal wave. These are the regions of rarefaction, and this is the regions of compression. This darker ones here, these are where the particles are packed together. These are regions of compression, or the springs. Now, when we compare the transverse and the longitudinal wave, where there is a crest here, we could compare it and say it is similar to a rarefaction, and where there is a trough here, then we could say it is similar to a compression. And now the distance between a crest and a crest, consecutive ones, or a trough and the next trough is wavelength. Similarly, the distance from a point of rarefaction to another point of rarefaction is a wavelength, or a point of compression to another point of compression is wavelength. Now, the above mentioned or explained were types of progressive waves, and we said that a progressive wave is a wave which transfers energy from one point to another. Now, the wave which is not progressive is called stationary wave. And so now let us look at stationary waves. Stationary waves, which are also called standing waves, are waves produced as a result of superposition of two waves with equal amplitude and frequency, traveling at the same speed but in opposite direction. Now, the word superposition here simply means that the two waves will meet, and this superposition it will be superposition of meeting, merging two progressive waves which have equal amplitude and equal frequency, traveling at the same speed but not in the opposite direction. But note that they must travel in the opposite direction. When they are traveling in the same direction, even if they merge or superimpose, they do not form a stationary wave or a standing wave. A standing wave is only formed when two similar waves, similar in that they are having equal amplitude, equal frequency, traveling at the same speed but in the opposite direction. So the scientific word we use for merging here of the waves meeting is superposition or superimpose. Now, how can we really acquire similar waves to merge? So the waves are set up, and when a wave reflects back from a surface, the reflected wave interferes. When it is reflected back, the reflected wave will interfere with the wave still traveling in the original direction. When that happens, this wave, which has moved from left to right, meets with a similar wave which is moving from right to left. Okay, they have the similar amplitude, frequency, but traveling in opposite direction. When the two superimpose, then they form a stationary wave, and this is an illustration diagrammatically of a stationary wave. What are the examples of these stationary waves? We find them waves in stretched strings and waves in pipes. What are these stretched strings? Let's look at a guitar. Fixed at both ends. The string of a guitar is fixed at both ends and it is stretched. So that forms waves in stretched strings. Then we also have waves in pipes. Pipes can be open or closed. When you say open pipe, then it means it is open at both ends. But when you say closed pipe, then it is open at one end and closed at the other. So we have instruments that use such pipes, or call them tubes. And when you disturb the air in those pipes, you form stationary waves. Good. Now, having looked at progressive waves and stationary waves, what are the differences? We can now look at the differences between the two. I have my table there. to show the differences. One, let's look at the amplitude of vibration of the particles is constant. The amplitude of vibration of the particles of a progressive wave is constant, whereas on the side of stationary wave the amplitude varies with the distance. As the wave moves, the amplitude is not the same. Now, amplitude is the amplitude is the maximum distance. When you look at this wave, the maximum distance of or the maximum displacement of a wave particle from the rest position, the maximum displacement of the wave. When the wave the medium is disturbed, a particle vibrates, or it gets displaced from its original position. The farthest it can reach that point or that distance or displacement from the rest position is called the amplitude. So for progressive waves, the amplitude remains the same as it moves, it is constant. But for stationary waves, the amplitude varies or keeps even reducing as the distance, as the energy moves or the distance increases. 2. Progressive waves transfer energy from one point to another. We talked about that. But stationary waves, there is no transfer of energy. There is no transfer of energy. There is a phase difference between the particles for progressive. The phase difference between the particles of the medium is the same, but the amplitude is different. The wavelength equal to the distance between two successive crests or troughs for progressive wave, but for a stationary wave, the wavelength equal to twice the distance between two successive nodes or antinodes. Now, what are the nodes or antinodes? Let's go back to our diagram. These points here are called antinodes. That's why we have represented them by letter A. They are antinodes. And these points here on the rest or equilibrium position here, they are called nodes. We are using letter N. Now, the distance from a node to a node, to consecutive node, is a half wavelength, while the distance from antinode to the consecutive antinode is half wavelength. So to have a full wavelength, it is the distance from this antinode, leave out this one because this is half, then you go to the third. That is the wavelength of a stationary wave. But for a transverse wave, we ignore this dotted wave here, which is the reflected wave. Then we look at the one which is solid, and it is the distance between these crests. Now for the transverse, for the progressive, this will be not antinode, but to be a crest to the next crest, which is consecutive, and that is the wavelength. We're trying to look at classification of waves and their differences. That brought in the terms that we seem not know, but at this time let us look at the terms which are used in waves in a more clear way. And for us to understand the terms, we shall need to know this progressive wave and label them, label it, and then this will help us to understand the terms that I've been talking about, like wavelength, amplitude, crest, trough, and so on. So our first term is amplitude. As I mentioned earlier, amplitude is the maximum displacement of the wave from the rest position. This displacement here, this distance here is called a displacement. From here to here is the maximum displacement of the wave from the rest position of the wave. What is a crest? A crest is a point of maximum displacement from the rest position. These points here, this point, this one, and this one here, are points of maximum displacement and they are called crests, while these lower points here are points of minimum displacement and are called troughs from the rest position. What's the rest position? Is this horizontal line which we are calling, if the medium was not disturbed, then these particles would were settled here, but when they are disturbed, they get displaced, and the point of maximum displacement they can reach is called a crest, and below it, minimum displacement below the line is called a trough. Wavelength, that one I've already talked about it. It is the distance between two successive crests or successive troughs of a wave. I have showed you on the diagram successive crests or successive troughs of a wave. Successive means one after the other. Period, we use symbol capital T for period. I've not been mentioning about symbols. Lambda, wavelength, we use symbol lambda. This symbol here is called lambda. It's just a Greek letter, but we know it as wavelength. Then for period we shall use capital letter T, and from the word period it's about time. So this is the time taken for a wave to complete one cycle. The time taken to complete one cycle by a wave is called period, and it is measured in seconds. And in frequency we shall use small letter f. And this is the number of cycles or number of oscillations made by a wave per second. In just 1 second, how many oscillations or how many complete cycles did that wave make? Then that number of complete oscillations in that 1 second or per second is the frequency of the wave, and the unit for the frequency is Hertz, capital H, small z. And there's a relationship between frequency and period, and frequency is equal to the reciprocal of period, which is 1 over period. F is equal to 1 over t. 1 over t. You have to master that, because you will need it. The speed, yes, the wave moves, so therefore it has speed. And how can we obtain the speed, or what is the speed of the waves? Just like you define speed, it's the distance traveled by a wave per second. The distance traveled by a wave per second, or the distance the wave travels divided by the time taken as a formula. But for the diffusion, it's the distance traveled per second. Waveform is simply the shape of the wave. Okay, like I showed you a transverse wave and a longitudinal wave. So that is a waveform. The shape of that wave is the waveform. And phase, these words are going to be used and you have to know them. This is a particular point in time on a cycle of a waveform. A particular point in time on a cycle of a waveform. Let me take you back to the diagram. at a particular point, at this point or at any point on this wave cycle of this wave shape or form. That is the phase of the wave. At any point here where I am pointing anywhere, at that point, at that time, at that point, we shall get the phase of the wave. Look at this. About a cycle. A cycle or an oscillation is a complete to and fro movement of a wave particle. We said the particles vibrate, move to and fro. So when it goes and comes back, it has made a complete cycle or a complete oscillation. Wave front. I talked about ripples in the introduction, but those ripples form what we call wave fronts. Now, a wave front is a line or a surface drawn in an advancing wave in which all particles are in phase. These concentric cycles, they see in this picture here, are called wave fronts. In this picture, these are wave fronts of water. So a line or a surface, or you can call it a curve, drawn in an advancing wave in which all particles are in phase. The particles which are vibrating at this point have the same phase, or they are in phase. When you look at this other one here, which is a bit far, all the particles at this point here are all vibrating in phase, and therefore when we draw a line there or a curve through that, or like the way it is illustrated by this ripple, and this is now the wave front. Diagrammatically, when you just draw, we represent them with cycles. These are wave fronts. So we have circular wave fronts and we have plane wave fronts, which are just straight. So when you hit a straight bar in water, it will produce straight or plane wave fronts. Now these are plane wave fronts, but these are circular wave fronts. These are just diagrams to illustrate the two types of wave fronts. And please note that the distance between two consecutive wave fronts is equal to wavelength. The distance from here to here is wavelength, or from here to here is wavelength. When I come to this side of figure B, from this wave front to this one here, this distance here is equal to the wavelength of this wave, and even here the distance is equal to the wavelength of the wave. Now, velocity of a wave. Shall look at the formula derivation. We said velocity is the distance moved per second of a wave. So there's a formula for a velocity of a wave, which I'm going to show its derivation and we'll get to know the formula. We say suppose a wave makes n cycles or n oscillations in a given time t, and in that it has covered a distance d. So how shall we get the velocity or the speed? Of course, the speed is equal to distance covered over time taken, which is d over t. But d is equal to n lambda. Lambda represents the wavelength, n the number of cycles. If the total distance moved is d, and each complete cycle covers a distance lambda, which is wavelength, then the total distance in terms of the wavelength will be the number of cycles times the length, which is n, where lambda is the wavelength. How about the time? We said period capital T the period capital T is the time taken to complete one cycle, or the time taken to complete one wavelength. So therefore the total time also is equal to n times the period, which is T. So when you substitute in our formula, of velocity equal distance over time, we have n lambda over nt. The n will cancel out, and we shall have v is equal to lambda over t. But also remember the relationship between frequency and period. We said f is equal to 1 over t. So 1 over t here, 1 over t, there's 1 here which is not visible here, but you know mathematically there's 1 over t is going to be replaced by f, which is the frequency. Hence the velocity of a wave is given by v is equal to lambda f, or f lambda f, the wavelength times the frequency. Alternatively, we can just consider a wave that makes only one cycle. One cycle from O to this point here is a half a cycle. From here to here is another half a cycle. So a one complete cycle is from here, you move up to here. So this wave has made this complete cycle, one complete cycle. If you go beyond here, then you are making another cycle. But we shall stop here. We are going to consider only one complete cycle. The distance moved from this point to this point by the wave, since it is one cycle, it is the wavelength lambda. And the time taken, this is horizontal is represented, the time taken from O, origin, to this point where it completes one cycle is equal to the period by definition. So if we consider distance moved in one cycle is wavelength, and the time taken to complete one cycle is period, what will be the velocity moved in only one cycle? Velocity v moved in only one cycle is given by, of course, it will be the distance moved in one cycle, which is the wavelength, over the time taken in only to move one cycle, which is the period. So this, members, gives us v is equal to lambda over t, and again f is equal to 1 over t, giving us, hence our formula is v is equal to lambda f. Please, you have to know how to derive this, or please make sure that you know this formula here for velocity of a wave, or the speed of a wave. Dear students, or student who is watching this video, let's now look at the examples, or the mathematical examples, which help us to understand the terms, or to utilize the terminologies that we have met, and also the formula that we have just derived. And our example number 1 is calculate the frequency of the wave if its velocity and wavelength are 5 meters per second and 0.5 meters respectively. Velocity and wavelength. The solution: we have been given velocity 5 meters per second, wavelength 0.5, and we are required to find the frequency. These three factors, or these three, are in our formula. From our formula, which is v is equal to lambda f, we are given v, which is 5, we are given lambda, which is 0.5, but we don't have f like I've illustrated here. So we just substitute 5 is equal to 5 is equal to 0.5, f, and when you get f, you do divide 5 by 0.5 and you simply get 10. Remember, the unit for frequency is hertz, capital H, small z. So we get the frequency of that wave being 10 hertz. Example 2. A vibrator of frequency 50 hertz produces circular waves. A vibrator of frequency 50 hertz produces circular waves. If the distance between two successive crests is 3 centimeters, two successive crests is 3 centimeters, find the speed of the wave of the waves. Our solution. What do we get from the question? We have been given frequency. Frequency is clear there, 50 hertz. But they said the distance between two successive crests. This is the definition of the wavelength. This is the definition. That means the wavelength is 3 centimeters. Now, the wavelength equals 3 centimeters, which we should convert to meters. And here I've used wavelength equals 0.03 meters. When you change 3 centimeters to why? Because we have to obtain velocity in meters per second, but the wavelength is given in centimeters, so you have to convert it to the standard unit, which is meters. Now, using the formula V is equal to lambda f, V is equal to lambda f, we shall just substitute 0.03 times 50, and our answer is 1.5 meters per second. This should be a superscript up here, 1.5 meters per second. So from the question you should extract the important factors, the factors given to you of the formula that we expect to use, and you find what is missing. Let's look at number 3. A vibrator with a frequency of 20 hertz vibrates for a distance of 25 centimeters in 5 seconds. Find Roman 1, the speed of the wave produced. Roman 2, the wavelength of the wave produced. In our solution, I think, dear students, you can already tell what is given. The frequency here is given, the distance is given, and the time is given. From distance and time, what can we obtain? Distance and time. So speed, formula of speed, distance over time. Definitely now distance is given and time is given, but remember the distance is given in centimeters. This is 25 centimeters, must be changed to meters, so we have changed it here, 0.25 over 5, which is the time, which is in the right unit, which is seconds. So 0.25 divided by 5, and we get 0.05 meters per second as the speed of the wave, solving Roman 1. Roman 2, Roman 2, we need to get the speed, we need to get the wavelength, and this is a question. V is supposed to be f lambda, please correct that, f lambda, which is the wavelength times the wavelength times the frequency, not the period. So when you substitute the speed you had already obtained, the wavelength is not given, which is actually the one required, but the frequency was given. So this, please make a correction here, this is supposed to be frequency f. So 20 times lambda, and lambda is equal to this 0.05, which is our speed of velocity we obtained, divided by the 20, and we get the answer as 0.0025 meters. 0.0025 meters. That is now example 3. Hope you're following me. Let's look at example 4. A vibrator produces waves which travel a distance of 40 centimeters in 2 seconds. A distance of 40 centimeters. If the distance between two successive crests is 5 centimeters, find Roman 1 the velocity of the waves, Roman 2 the frequency of the waves. Again, when we try to digest or interpret the question, consider that our distance here is given in centimeters, so here I have converted it to meters, which is 0.4 meters. The time is in 2 seconds, that is fine, but the distance between two successive crests, again from the definition of wavelength, it's the distance between two successive crests, which is 5 centimeters, converting it to meters, 0.05 meters. Solving our first question, velocity is simply d over time, distance over time. Now in the question you can see where you use velocity is equal to f lambda, or where you use velocity is equal to distance over time. So you must know, we must see what is given to use in determining what is required, like velocity. And then when you substitute, you get 0.4 over 2, and you get 0.2 meters per second as the velocity of the wave. And now how do we get the frequency? Now here we use d over t, but because we need frequency this side, now we cannot use it. It is not, to not be help to use that formula, and we have already used it. So we now need its value, the value we have obtained for velocity, which we're going to substitute here. Substitute for wavelength, which is this one, and then be able to determine frequency. We need to have 0.2, which is our velocity, is equal to f times 0.05, and the answer will be 4.0 hertz. Yeah, so those examples are illustrating. Let's continue to our example 5. If the distance between 5 successive crests, now we have been talking about only 2, now here it is 5. The distance between 5 successive crests is 100 centimeters. Find the wavelength of the wave. Now in the solution I'm trying to illustrate the crests. This is 1, 2, 3, 4, 5. So these are 5 successive crests, and the distance between the distance is from here to here, from this first one to the 5th, is 100 centimeters. So since the definition of wavelength is the distance between two successive crests, then it means from here to here, this is, we have one wavelength, another wavelength, another wavelength, another wavelength. How many wavelengths are here? You can see 1, 2, 3, 4. So the 5 successive crests actually have 4 wavelengths. So we shall just simply say 4 lambda, which is 4 wavelengths, is equal to the distance between which is equal to 100, and we shall get the lambda being equal to 25 centimeters as our answer. Alternatively, we could use a formula that the distance given over n minus 1, n becomes the number of the crests which are successive. N is the number of successive crests. So when I substitute in that, then we have 100, which is the distance, over n, which is the crest, the number, minus 1. Because here you can see the way 5, but the number of wavelengths we got here are 4. That means we reduce by 1, and that's why I'm saying 5 minus 1, and we shall get lambda equal to 400 over 4, getting us our answer as 25, just like here. So this is just more to be more elaborative and to give you a standard formula, but here also when you illustrate like this and account, you see 4 lambda is equal to 100, and you divide, you shall get 25. Good. Number 6. The figure below figure below shows a wave spreading out from a point. Find the wavelength of the wave. Now this is the figure, and from here to this last wave front is 12 centimeters. They want us to find the wavelength. Each space from the source between the wave fronts equal to the wavelength. What do I mean? From here to here, like, is the wavelength. Also I said two consecutive wave fronts, the space between them is wavelength. So from here to here is another wavelength. This is also another one. This another. So how many wavelengths are here? 1, 2, 3, 4. Hence there are 4 wavelengths, and the 4 wavelengths give us the total distance, which is 12 centimeters, and therefore lambda is equal to 12 over 4, giving us 3 centimeters. I repeat, the distance between two consecutive wave fronts is equal to wavelength. I mentioned it earlier, but the wave started spreading from this point, and therefore it has moved a wavelength from here to here. Add this one, those are 2. Add another wavelength, these are 3. And this one, these are 4. 4 wavelengths equal the total distance 12 centimeters. So 4 lambda is equal to 12. So divide by 4. 12 divided by 4, we shall get 3, and that's how we work out that one. Number 7. Trying to give you enough examples to illustrate different questions. The figure below shows a transverse wave which covers a distance of 48 centimeters in 0.8 seconds. Yes, we made a transverse wave. This is a transverse wave, and they're saying this distance, this covers a distance of 48 centimeters in 0.8 seconds. What are the questions? Find the amplitude, the wavelength, and the amplitude, the wavelength, the speed, the frequency, and the period of the wave. Okay, so from our definitions, amplitude is the maximum displacement of the wave particle from the rest position. From here to here is the amplitude, and the distance from here to here is 8 what? The unit is here, so 8 centimeters. So therefore A is equal to 8 centimeters. It is 8, then the unit is given 8 centimeters. 80 centimeters. Now let us look at wavelength. Wavelength from here, we said the distance moved by a wave in one complete cycle. So if we start from the origin, from here up to here is a half a cycle. From here up to here is another half. So what distance from here up to here? It is what? 24. So we shall see that the wavelength is equal to 2 lambda equal to 48. Again, let's illustrate. Now if from here to here is wavelength, and from here, this is another cycle, from here to here is another cycle. So how many cycles are here? There are 2. They have covered. These are 2 complete cycles which make 2 wavelengths, and the total distance is 48, and that's why I will say the 2 lambda is equal to 48, and we get lambda is equal to 48 over 2, giving us 24 centimeters. But you could still changing it to meters, 0.24. Or the same, you could still just read it from the diagram itself, since you can interpret that the wavelength is the distance moved in only one cycle, and you can see that in one cycle it is 24. The unit is here, so it is 24 centimeters, which is just the same as what I have obtained here. The third question is speed, distance over time. Frequency is not given, much as we have got wavelength, the frequency is not given, so we cannot use the formula of f lambda. We can utilize the formula of distance over time. And what was the distance? We move back and I show you the distance. The distance is given here in the equation. Distance is 48 centimeters and the time is here 0.8. So this 48 has to be converted to meters. So we have converted it to meters, which is 0.48 over the second, which is 0.08, getting us. We can cross check the answer, which is 6.0 meters per second, and that is our the speed of the wave. We were also asked to find frequency, and here, since you have already obtained wavelength, you have obtained velocity, you just use the equation of the wave, which is v is equal to lambda f or f lambda, depends on what you prefer. So this is 6, which is the speed or the velocity, 0.24. That's why I converted it to meters, because I'm going to utilize it here. Okay, yeah. But for the final answer, even if you had not converted, we would give it correct. But when you are substituting here, whenever there is a substitution, dear student, whenever there is a substitution, make sure you are using standard units for meter, for speed, and for wavelength. Okay, so when you simplify that, f is equal to 6 over 0.4, giving us 25 Hz. 25 Hz. And the final question is period. We utilize the relationship between frequency and period. You have to remember this, that the period is 1 over f, or f is 1 over t. T is 1 over f, or f is 1 over t. So just interchange them, and then so here we have f, so just say capital T, which is 1 over 25, and we get our answer, which is 0.04 seconds. I have to emphasize units. Whenever you write the final answer, make sure they are units. Speed, meters per second. Wavelength, I have put meters. Frequency, I have put Hz. So even you, when you are calculating what you are asked to calculate, and it is a physical quantity, each has units, you must include the unit, dear student. Okay, let us look at another question. That figure is given, that the diagram shows a progressive wave. Determine period, frequency, wavelength, and speed, just like we did. Again, period. Look at the diagram. This time here, you can see that our diagram has time on the horizontal axis, as opposed to the previous diagram where we had the distance. Now when you have time, then this graph is going to tell us the period by definition. The period is the time taken to complete one cycle, and therefore just if the wave started from here, this is a half a cycle, this is another half. So a complete cycle moves from O, or from 0 up to 4. So therefore the time, since this is time, so therefore this is period. So our period, just read from the diagram and say t is equal to 4 seconds, and the unit is here, seconds. Frequency. Now frequency, you cannot read it from the diagram, just have to remember the formula. Just have to remember the formula of frequency, that f is equal to 1 over t, and substitute. Now substitute for f 1 over t, then you get the answer. I will not calculate this one here. You can now complete this one. You can calculate f is equal to 1 over t, and t is this, so we just substitute f is equal to this 1 divided by this 4, and you get the answer. Wavelength. Again, look at now the distance. The distance is given up here, this time not on the horizontal axis, but it's given, but they are stating that from here to here is 200 meters, from the origin of the wave to where it ends. So we just ask ourselves, how many cycles has the wave made, or how many wavelengths has the wave made? Now this is one complete cycle, this is the second, they are therefore 2. So we just say 2 lambda is equal to 200. Divide 200 by 2, you can get wavelength as 100. And we look at speed. Now simple, we shall get if we calculated, I think we got 0.02, so 100 times 0.25, and we calculated, we got 0.25. so substituting this 100 times 0.25, we shall get our yes. So this is finally, I had hidden this from me, but now I brought it, that f is equal to 1 over t, which is 1 over 4, and I get that. So when you carry this and substitute in here, and you get our velocity of this wave, in particular being 25 meters per second. Dear students, that has been my lesson for you, and the introduction of waves and calculations in the waves, and these are the exercises that you should do, and make sure you practice, work out these exercises. Keep pausing, you copy the exercise, pause, you copy the exercise, and you do all these exercises to kind of consolidate the work that I have taught, consolidate the work that I have taught. These are good numbers to illustrate the concept, and at the end of my lesson also, I will require you to summarize what have you learned from this lesson of introduction to waves, right away from the beginning. You can just write down, say for example, we began with introduction of waves, trying to bring up a definition of a wave, and say we write a definition of a wave. What else did you learn? Just cite, you say looked at the types of waves, maybe what are they, something, and evaluate yourself whether you've understood. Went further, deriving the formula of the velocity of a wave, going into examples, all those things. Just summarize and evaluate whether you have understood them. Work out these exercises from one. Exercises start from exercise 1, that one there, and you go to 2 and 3. All these numbers illustrate what I have taught. And number 4, if you have understood what I have taught, exercise number 5 and 6, and by the time you complete these 8 questions, I believe you have understood what I have taught today. And next time when I'll be talking about the properties of waves. Thank you for listening, and I hope you enjoyed the lesson. I remain teacher Wanda